I don't know how I left off last video, but I remember saying like, oh, I should do exercises on matrix calculus. That is the focus of today. Is I had Vault Chat's agent make a markdown file that goes from linear regression all the way down, all the way up to LLM in terms of the chain rule for backprop and the fancy, not the fancy, but like the new notation that's required in order to keep it all in your head of what's going on. So like it starts with like, yeah, it's matrix calculus and like the Jacobian, which is like super cool. Cause like I remember learning the Jacobian or using the Jacobian in multivariable in calculus, and like we used it to transform and change our space from um Cartesian coordinates to polar coordinates. And like that's like so freaking cool, you know? And that's a bit separate. Like even though it's got like the same title of like a matrix of partial derivatives that like captures how a space is like transformed. Um and like, when I first learned the Jacobian, I knew I rocked with it. I knew it was like I thought that it was like really cool. Um and I wish that like I could do a video where I just like, I don't know, studied the Jacobian. And then like, even more so, still the Jacobian is how um they found like the J space for Claude. That's like super cool. And then the Jacobian conjecture being disproven is extremely heartbreaking. But whatever. It still holds in the majority of cases, which is completely fine for practical applications. But it's, unfortunate that it's not purely correct. Um, and I wonder what the term for the conjecture is. Is the conjecture that if you have like a transformation, um, how do I say? If you have a transformation for which the determinant is non-zero, then the mappings are all one-to-one. And then the counterexample is that there is a projected point in which 2 points go into for a non-determinate matrix or whatever. What do you mean a non-determinate? For a matrix with a non-zero determinant. So an invertible matrix, a unique matrix, right? Um, yeah, I think so. Um, we're not going to clarify that. I've made linear algebra mistakes before. I'll clarify my definition of invertible or non-invertible matrices later. Um, and then last tangent is like, I think it's because like, how do I say, that notion is around square matrices, but like I feel like the Jacobian is not necessarily a square matrix. I thought you could do, you know, 3 coordinates to 2 coordinates, but maybe not. I guess when we did it from Cartesian to coordinate, we went from x and y to r and theta. So technically that is square. So unknown for me right now. Let's get into the practice problems. I think that's where we're done. Let's just like jump straight into it. Let's see. Exit full uh, and come up. Okay. I'm trying to be a little bit more professional, you know what I mean? I had it prepared before the video. Isn't that fantastic? And this whole setup is prepared. I was like, oh, we have windows. I think I can do this. It's like, you guys get to see my lovely face in the upper right hand corner. And then I get to read these things on the left. You guys get to read them on the left. And then I have my iPad. I'm going to write here. And you can see whatever I do. So hopefully that's like calm to follow along. Hopefully my rant didn't go on so long that, I don't know, your attention is gone and you don't get to this fun part. It's like, oh, dude, this could be like an actual YouTube video. Um, but yeah, like, hopefully this is an actual YouTube video, and we have fun. So yeah, let's get straight to it. Fortunately, we're using the same example, um, of logistic regression to, of single-headed logistic regression to multi-headed logistic regression to neural network to large language model. So let's just read it first. So the purpose, backpropagation from scratch, logistic regression to LLM. Perfect. Okay. Purpose is to build up from logistic regression to a language model on one shared foundation, performing backpropagation by chain ruling a scalar loss back to every parameter. Perfect. Each rung reuses the mechanics of the one before it. Perfect. So by the time you derive the neural network, you're practicing the logistic regression steps again inside a bigger object. That's just regurgitating what I said, because this is the structure that I believe that should exist, that should be possible, but it's just telling me what I told it to make. But whatever, that's fine. I don't care. How to use this doc. Every rung gives you the setup, the notation, and the forward pass. As for notation, a whole bunch of stuff, whatever. You perform the derivatives and the self-test. Each new piece of notation and every new tool is defined in the rung where it first appears. Again, I asked for that. And the step that needs it. Nothing is front-loaded. It tried to front-load things. Whatever. So let's see. Let's start with this normal logistic regression. Hopefully we can speedrun this, because this would almost be attempt 3 ongoing at this. Is one linear unit processing or producing one probability trained on one example. I don't know why we're saying one example. This is the whole backprop pattern on the smallest possible object. I think I can agree with that. Is x is our vector. Is that why it means a single example? We're going to ignore that. X is our input vector. W is our weight vector as a single row, even though W could be a matrix, whatever, you know. Z is our pre-activated scalar. Sigmoid of Z squashes it into a probability. And then we denote our intermediate variable A equals sigmoid of Z to make the partial derivatives easier, for which we will see soon, hopefully. Y is the true label, and then L is the loss. We use binary cross entropy, classic. I'm not going to go over that. You can watch a YouTube video on the cross entropy formula. It is large when A is far from Y and 0 when A is close to Y. Perfect. What we want from a loss function. Forward pass is X. I don't like those arrows. Nothing's being implied. But I guess it's not double arrows. Still, I don't like it. Yeah, so first we have X, and then we do X times W plus B. We get Z. We activate Z, and then we put that A that's highlighted in our loss function with Y. Mechanism, the chain rule. Backprop is nothing but the chain rule. Cool, cool. Loss with respect to W's is loss with respect to A times A with respect to Z, Z with respect to W. That's perfectly fine. I'm not sure. I think I'm fine with that because, like, I understand it now. I don't know if the documents explained it to me the way I would like for the document to explain it to me well, because eventually we're gonna do something that I'm confused on and I don't know, and I would like the document to contain like the details. Again, even more fortunately, VaultChat is awesome. We can do inline edits, and when the time comes, hopefully we'll, or ideally I wouldn't have to use it, but we'll probably end up using it, and then I'll get to show it off. Tool you need for the activation link. Sigmoid can be clean derived. Sigmoid prime, yeah, fine. Tool introduced at the step is the transpose. Yeah, it's the transpose of X. It's like weird. At the last link, you differentiate the scalar Z by the vector W. And this is where I don't know if I did this in a video. The denominator notation comes in. By the vector W, the result must carry the shape of W, and that is by following the denominator notation. So that the update when we do backprop type checks, which means that the shape of the derivative aligns with the shape of the actual weights, which by choice it doesn't have to. Writing Z equals you're talking about indices, yeah, it's a dot product plus B, because B is going to be a scalar. Taking it gives a row vector. Since X was defined as a column, see, I'm not really sure that gives you a row vector. That's part of why it's like whooshy for me. I don't think it gives you a row vector. I'm going to say that we're doing scalar level derivatives and that we can package those derivatives however we please as long as the order is processable, because every single derivative has has a way to be identified, and it's just easier if we shape it as a whole so that it all smushes together. When we could represent the same numbers by this, you can rotate numbers of information. There's no change in the information. You're packaging it differently, but then you don't get to do this. So that's a choice of how you're going to contain. In the same sense that, like, a tensor isn't really a tensor. It's a really long vector. You know what I mean? Same information. It's a choice on how you're going to package it because everything can be identified completely fine. So this is almost a computer decision. X transpose, your derivation, work backward one link and produce, work backward one link at a time and produce all of L with respect to A, L with respect to Z, L with respect to W. This is what I'm responsible for. Watch for your cleanest result. Wait, what? Watch for the clean result at loss with respect to Z. Confirm the shape of L with respect to W matches W. Your work. Self-test. Replace. Explain why or why not. Oh boy. Okay, so let's try it, I guess. So our goal, we want all of it, right? Yeah. Is, what's it called? Yeah, there's actually so much going on. There's so many things that we're going to calculate. So L equals, oh, you can't see that. How am I going to do this? Let's see. I also think that's, oh, but it's a good size for YouTube, so I might go with that. Okay. Let me give myself a little marker. Okay. And then the end of it for you is, oh. Oh my goodness. No, dude, come on. Okay. Cool. And then the bottom should be fine. I don't know. I'm going to choose to not zoom. I'm going to tell myself to not zoom, and then I'm going to stay in this box, hopefully. Let's see, last thing. And then loss, let's do 4L. Okay, fine. So first we're going to say loss. Are we going to do the original one first? Sigmoid is messier. Oh no, cross entropy is messier. I don't want to take the derivative of that. Do we do it for the love of the game? This derivative is so much easier. Oh, it's mean squared error. Dude, that sounds like a deal. Oh, it literally says squared error. Come on, man. And redo. Let's see. So first we're gonna say L. Yeah, L equals 1/2 of, let's see, of A minus Y. What it didn't explain for me is the fact that A is a deliberate intermediate variable that is actually kind of a function. And like is a decision we make. Because it makes this something that we can do with respect to A. But if you did it with respect to sigmoid, you would immediately want to finish it, I guess. Yeah, because how do I say? Because you can do it like L, you can do partial of L with respect to A, and you could call it a day if A is all you cared about. Because this is now what you, like, if this is like, it's not decision variable, but if this is the parameter that you're able to shift, even if it is a function, you wouldn't go any further because this is where you're going to choose to shift, is even if A equals sigmoid of Z, if A is where you're controlling, it also kind of doesn't make sense that A equals sigmoid of Z. So there's a few things going on. But you would just stop here. It's like, okay, now you know what you want. You have your gradient to perform descent with. But if you wanted to do it with respect to Z, then you do need A with respect to Z. And sort of when we do sigmoid prime, what's it called? We by default are going to take by default, we do the chain. You know what I mean? We sort of like, I don't know. We chain rule all the way. And it's still not clicking for me yet. I don't have an intuitive representation for it. I can like understand that it works and that there's like a clear motivation, but yeah, it's not. I couldn't. I don't think I would confidently like rederive it as in like a, oh well, obviously this is how you would do it. Yeah, okay, let's call it there. Let's see. So what's the first thing we want is the partial derivative of L with respect to A, which equals 2 times A minus Y times nothing. What's it called? Times 1. There's nothing. Yeah. Okay. Importantly, the y is still there. So this equals, yeah, 2a minus 2y. And then partial derivative of L with respect to Z equals the partial derivative of A. Nope. Equals the partial derivative of L with respect to the partial derivative of A times the partial derivative of A with respect to the, wait. Again, if I'm saying the words for partial derivative incorrectly, please don't mind me. I'm still learning. With respect to Z. And then we can just take the product of this. And then like there's a part of this for like the autograd graph that we're supposed to add things. And it has yet to, this hasn't been shown to me in this doc yet. So we may find out that I'm going to get confused. Maybe, I don't think we're going to see it in the multi-output logistic regression. We may not see it until the large language model, which is bad, which means the document needs to be worked on. So I might interject and ask for a lesson on autograd. I can already feel the part 2 coming. Let's see. That's with respect to Z, okay, and then with respect to W. So Z equals WX plus B. So partial of L with respect to W equals partial L with respect to A times partial A with respect to Z times partial how do I say partial Z with respect to W. Oh, this is getting like very familiar. I've definitely done this before. Partial of L with respect to, how to say it? Partial B equals partial L over partial A, not plus, times partial over partial Z times partial Z over partial B. Yeah. There's something going on here. I recall this. I did this. I've done this before. I said I'm not going to zoom. I lied. But like we're already doing it here. You know what I mean? And so we have the first main one, fantastic, and then that immediately points to here. So then what's A with respect to Z? We have A equals sigmoid of Z, which means that partial of A or partial Z equals sigmoid prime, which equals sigmoid of Z times 1 minus sigmoid of Z, which is exactly what we would put here. And then that drops down. That's completely fine. Z with respect to W is still going to be X transpose. So let's see if things line up dimensions wise, because that's very interesting as well. These are scalars. This is a scalar, this is a scalar, this is a scalar, scalar. You can do scalar times vector and we'll be fine. And this will have the correct shape, which is what we expect. It's the same shape as W. Good. And then with respect to B is scalar, scalar, scalar. Because with how do I say? Z with respect to B is 1. So fantastic. Oops. Yeah. Z with respect to B is 1. Yeah, I think that's it. I'm sure we can go further. This is motivating to me to do autograd exercises. Oh, this is motivating me to do autograd exercises where like I'm given a function and I'm told to draw the autograd graph. But that's not what we wanted to do today. So, um, I think that's it for today. Or not, not for today. Like, yeah, I think that's good for the first one. Is like, let's continue to move forward because that was supposed to be the basic one. Let's not fully erase it. Okay, let's see. Context predict M classes at once instead of one. Same thing as rung one stacked M times. I don't know if that's actually true because I told it that's what I think. So like, I still think I'm right, but like I don't know. This is the first rung where parameter is a full matrix. Notation, weight matrix, bias vector, pre-activation still a vector. M is the number of classes, perfect. Activation is an element-wise activation, perfect. Tool introduced here, the element-wise. Oh, okay. I know the symbol as element-wise. I think that's all we need to know. Is the Hadamard product. I don't know. I haven't learned it in class. I've used the notation though. Barely, at best. I've seen it. Sorry. When a function is applied to a vector, one component at a time, like sigmoid is on Z, its derivative is also element-wise. Two vectors combined component by component are written. Does that produce a matrix? Vectors combined component by component are written with U Hadamard equals UI VI. Oh no, that's a wait, no, now you're confusing me. How is that not a dot product? You'll need it the moment you differentiate A with respect to sigmoid Z component wise. Wait, I'm confused. Two vectors combined component are written. Oh, oh, oh. It's doing the dot product without doing the addition. Is like, yeah, you're combining it element by element. Dot product is element by element, but we're not summing. Oh, oh. Okay. Another tool. We're already at the Jacobian. That's crazy. And run, you differentiated a scalar by a vector. Now you differentiate a vector by a vector. The object holding those partials is the Jacobian. For A, size M. Oh, is Jacobian a vector here? Oh no, it's still a matrix. Okay. For A, size M, and X size D. Okay. It collects every Yes. Yes. Every element of A with respect to every element of X, which is going to produce a matrix that is of the size of A with respect to the size of X. So element by element, single step derivative. Define its shape, in which partial sits in which slot before you use it. The chain rule generalizes. You now multiply Jacobians instead of scalars. That's something. Another thing, oh boy, tool introduced here, differentiating by matrix. Differentiating z equals wx by the matrix w is a new shape move versus rung 1's vector case. It's still not just transpose. The gradient of the loss with respect to w comes out as an outer product of the upstream vector with x transpose. I can see that. I can see how that might be possible. I can see how that's possible. Yeah, that's a lot to wrap your head around. Ah man, I don't know the best way to build this this math intuition. This is really something for me to sit with. Um, hmm. Yeah, let's go for it, I guess. Let's see. Is comes out as the outer product. Outer products are weird. It's x times x transpose. This is why it's good to have a linear algebra strong foundation. Um, of which I'm saying I don't have right now because I don't have a native per se intuition of outer products. So how would I say? You can write x. That barely you can barely see that. I never use the normal eraser. I should just get rid of it. How do I say? X x transpose, and I think part of this. No, part of this only works because you're assuming a particular sized. This is assuming this is the column. This is why linear algebra can be so annoying. This is assuming x is a column vector, I think. How do I say? Yeah, you need a d by 1 times a 1 by d. Or you can do by m. Sorry that we're using x in both. Is like you need a d by 1 and a 1 by m, and that'll produce a. And I don't know why, like. Oh. That'll produce a d by n matrix. And these are the vectors. Oh, but if you do x transpose, then it would be d. M and d would be equal in this case. Um, but you can do outer product with any column and then row vector. Yeah. So an outer product is the product of a column vector and a row vector. Um, so what was x transpose before? X transpose is the column vector. So what I want to form is the connection between the scalar and outer product case. Or I'm imagining the outer product case is the scalar case copied over a number of times, which is why it's m by d. M was just 1 before. Now it's, yeah, like m by d, that previous case is actually an edge case where m is 1. Writing z. Now, if we expanded that out, sure, let's go with x being a row vector here, is you would have, let's go with this. I wish I could copy from my laptop to my iPad. Is you have, how did we get to z? Let's say, I think we get to z the same way because z isn't activated. Yeah, so z still equals wx plus b. However, in this case, z is a vector. So we can also write z1, z2, and let's say m equals 3. Okay? Equals, and this is going to be a lot to spell out. So let's also say d, which is the dimensions of x, equals 2. We're going to do w, let's get this right. W must be a 3 by 2 matrix because it was multiplied by a 2 by 1 vector and added with a 3 by 1 vector to produce a 3 by 1. Come on. To produce a 3 by 1 vector. Ah, you can't see any of that. Sorry. I would prefer to move this up actually. Okay. So yeah, so this is, how do I say? This is, you still can't see that? Come on. W x plus b equals z. Okay. Wait, I'm actually realizing just now that's kind of crazy. I do the line in the z's now. I didn't always do that. I picked that up in college. That's second nature now. That's crazy. Yes. So W has 3 rows. So row by column is W1, 1, W2, 1, W3, 1, X1, X2, X3. Wait, no. It's X1 in every case. X1, X1 plus W, goodness, 1, 2, W2, 2, W3, 2, X2, 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 and then plus B1, B2, B3. Okay. And you know, like, this is hard because, like, even with me spelling this out, I do think that when I said we're doing like the edge case where m is 1, I think that hopefully that was like the beginning. But like even spelling this out, I don't know if that's immediately what's going to cause the click. But let's keep going. So in the edge case of m equaling 1, say we only have, what's it called? Say we only have this. Then, what's it called? Z, we're looking at partial of z with respect to w, okay, would equal, and we get to choose the shape. So trivially, we're going to say the row vector. Oh, no, it's literally x, okay. With respect to w is x1, x2, okay? And then because we choose the shape, that this is like, the representation that I'm going to say is like everyone is at a unique position and we choose the position in our tensor matrix, whatever, to capture the same partials. It's a notation structure decision. But the information has not changed because we're talking about the same relationship. The relationships are unchanged. The packaging is different and it's our choice. So then we could say, because we said at the start that X is a row vector. Oh. Well, no, see, like, that's what I'm saying. Part of also the pause is like the fact that we spelled out the multiplication as a, how do I say? Because I feel like here, X is a column vector, isn't it? Is that why? Wait, let's see. What does it say here? Is since since X was defined as a column, that row is written as X transpose. I think I think I can accept this. Yeah. So like X was defined as a column, and now we have a row because we read left to right. Um. Yeah. So which means that it's going to be represented as, or it's equivalent to X transpose. Yeah. Is like it's almost as if all new vectors are assumed to be row vectors until proven otherwise. And then X was proven otherwise because its initiation was to the right of W. And then again, B must be defined as a column vector because of its relationship with the other ones. But like, technically, you do addition left to right. There's no reason to say that that gives you a row vector. That must be some other convention that I don't like, natively have. Um, so same information, we're going to call it a row vector, and then we have X transpose. That's fine. We take it further. This is now just Z1. Hear me out. Hear me out. Hear me out. Hear me out. Okay. This is Z1, and we're working with indices. Unfortunately, I can't copy things, but if we do the partial derivative of Z2, derivative of Z3, gosh, you can't see anything, equals, ooh, I don't know how I feel about this. No. No, wait, yes, this would be fine. We're talking about W1. Yeah. But it would still be X1, X2. Because the shape of what's it called hasn't changed. Is X1, X2. And then like, but technically, this is the partial derivative of Z1 with respect to the partial derivative of W11. You know what I mean? And we've just packaged it so that it can fit into a vector. And we now call it this. And if we concatenated this one more time, we would say that therefore, therefore, the partial derivative of Z with respect to W as a whole is actually going to be the matrix X1, X2, X1, X1, X2, X2. Okay, I could handle that. I like that generalization. However, something's off. I need to ask. Oh, that's another thing. Is we're changing David's name to Tony. I think we're gonna call him Tony. Tony. I like the name Tony. So let's see. Um, is for this multi-output logistic regression, this um this m by d, which is what we've produced here, this is in fact m is 3 by d equals 2. Perfect. Okay. Where did the bracket go? Okay. Um, what's it called? We have the right shape, but I've also accidentally produced its contents. And let's see. The gradient of the loss with respect to W comes out as in outer product of the upstream vector. Self-test. Yeah. So this is my first question. Is I think I've done an m equals 2 case by hand. And what I saw was that it's just a copy. I didn't see of the upstream vector. What's the upstream vector? The upstream vector is z. Wait, but what am I missing? That's L with respect to W. So L with respect to W is, how do I say it? Partial of L equals partial of A over partial of Z times partial of Z. No, we're still missing it. Is it's partial of L with respect to A times partial of A with respect to Z times partial of Z with respect to W. So we're not done. We don't have partial of W, but what's partial of A with respect to Z? That's sigmoid. Sigmoid is operated element wise, and I think it told me I would need this. Yeah, yeah. Um, so it's, how would I say this? A with respect to Z is still sigmoid of Z 1 minus sigmoid of Z 3 times because it's element wise. There's 3 Z's, so there's M of them, so that's fine. And then L with respect to A is, if we're doing mean squared error, let's just say that it's 2A minus Y. Wait, I'm an idiot. There's no 2. I wonder if somebody saw that. There's no 2. It's 1/2 times 2. And I've known this. I've known this. What am I doing? Where did I make the mistake? Look at this. Look at this. What is this guy doing, bro? Yeah, it's just 1. And that makes a whole lot more sense. That's what I'm far more used to. It's like, yeah, it's supposed to be a clean thing. I was thinking like, yeah, because they do the half because of blah, 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 whatever. This guy's stupid. Silly mistake. Hopefully you caught it. Yeah, so it's actually A minus Y. Which is a scalar. So scalar times vector times matrix, and that would be um, L with respect to W. And okay, that's an excellent exercise. I think that like that connected things for me. I don't have I haven't done it routinely enough to skip ahead like that. But yeah, I think I'm okay with that. Is like that makes sense. And then like importantly, it's element wise. So this is Z1, Z2, Z3. It's one for each head. Um and then the thing that I want to clarify is Z with respect to W just a copy is like X transpose, X transpose, X transpose. That's sort of what I'm leaning on. So hello, David. Oh, Tony. Hi, Tony.
Hello, I am ready to dive into these backpropagation exercises with you. We
Yeah.
have the rung.
So I have a quick question. I'm working on rung 2 right now, and I'm curious about my self-test. I ended up doing m equals 3 and d equals 2, and um so what I did is I sort of worked backwards. Is I first did the partial derivative of z with respect to w, and what I did is I did like m equals 1 as an edge case, and I worked with like z1 equals w11 x1 plus w12 x2 plus b1, and then I wrote that that one solution is x transpose, and then when I spell it out for the further heads is I end up getting um, the exact same vector. I get x transpose 3 times. So I'm curious if the partial derivative of z with respect to w is actually just like x transpose x transpose x transpose. So it's sort of like a matrix that's like a, it's a copy of x transpose 3 times because we have m 3 times. And then the actual values become different because in order to get to the partial derivative of L with respect to W, um, that equals the partial derivative of L with respect to A times the partial derivative of A with respect to Z times the partial derivative of Z with respect to W. And the partial derivative of L with respect to A, there's that's actually going to be uh and maybe yeah, I think so. It's like I'm assuming that the operations are going to be element wise is the partial derivative of L with respect to A is actually element wise. Um is which means it's a vector times the partial derivative of a with respect to z, which is also a vector, and that vector is sigmoid of z times 1 minus sigmoid of z, and then that's times z with respect to w, and when ends up giving us the same shape, but the initial partial z over partial w is what I'm describing it as. And actually, I could use your help with that the chain rule part of partial derivative of L with respect to A and partial derivative of A with respect to Z, them being vectors. Um, in these cases, are we using the Hadamard product or something else?
Your intuition about the rows is spot on. For each class, the derivative of its pre-activation with respect to its own weight row is indeed X transpose. When you stack all three classes, you get three independent rows of X transpose. To combine these with the upstream derivatives, you do not multiply a 3 by 2 matrix directly by a vector. Instead, you use the Hadamard product first. The partial of L with respect to A is a vector of size 3, and the partial of A with respect to Z is also a vector of size 3. You combine these two
Sorry,
element-wise using the
sorry,
Hadamard
sorry.
product.
Hold on, I'm confused. Did you say the partial of L with respect to A is a size of 3, and then the partial of A with respect to Z is a size of A is a size of 3, and then you combine those with the Hadamard product, and then what? Hello?
Yes, I am here. When you combine those two vectors of size 3 element-wise, you get a single vector of size 3. We
What
call
are
this
what
vector
are
delta.
hold on, I'm confused. What are those two vectors though?
The first vector is the partial of L with respect to A. which contains the loss gradient for each of the three class predictions. The second vector is the partial of A with respect to Z, which contains a sigmoid derivative for each of the three pre-activations. Multiplying them element-wise gives you the gradient of the loss with respect to the pre-activations, which is a vector of size 3.
Okay, and then what?
Now you have a vector of size 3, which is your delta, and you need to multiply it by your pre-activation derivative with respect to W. To get the final matrix of size 3 by 2, you take the outer product of this size 3 delta vector with your size 2 input vector, X transpose. This outer product multiplies each element of delta by the entire X transpose vector, giving you exactly the 3 by 2 gradient matrix where each row is scaled by its class-specific delta.
Is that equivalent to performing the Hadamon with the... Oh, but you can't do element-wise if they don't match up. Wait, now I'm a bit confused. I understand that that's the shape that we want, but the partial of Z with respect to W is a size of 3 by 2. And then the partial of A with respect to Z is a size of 3. And the partial of Z of L with respect to A is 3. But like in the chain rule, at least what I'm used to writing is the partial of L with respect to W, and you spell it out with like scalar multiplication, but you seem to be doing something else, and that the forward and backward isn't consistent for me. So if you could spell that out at in the self-test section of rung 2, I would appreciate it, please.
I can absolutely write that out for you in the self-test section of rung 2. I will show you the exact step-by-step math starting from the scalar chain rule for a single weight, and then show how it naturally groups into the vector Hadamard product and the matrix outer product. Let me write that directly.
We got some reading to do. Let's see. Oh my goodness. We're not making it to the neural network. I'm getting hungry. Let's see. For any single class, Z, the pre-activation by the scalar chain rule. This is exactly what I have written. Beautiful. So let's look at each term. This is the definition of the outer product. Okay. I think this is where I'm going to call it. I'm going to finish reading this, but like after reading this and internalizing this, I think this is where I'll call it. I think it's a decent climax. Let's see. So let's write out the scalar of the chain rule for a single weight JW, the weight for class I and input feature, class J and input feature I, to see how the matrix operations emerge. For any single class, the pre-activation is yes. For K, yes. J, yep. The prediction and the loss. The loss is, yeah, that's across all of them. Okay. By the scalar chain rule, the derivative of the loss with respect to a single weight is yes. Let's look at each scalar term. L with respect to AJ is the jth element of the vector. Yes. Is m by 1. Sure. And then is the jth element of the vector yes. A with respect to Z is A yes. XI, but there's no XI. It's Z with respect to W. XI is the ith element of the input vector X of size D by 1. Sure, but that's not coherent. again, vault chat for the win. Let's see. Because you're differentiating z with respect to wi in that sum. Oh, yes. It equals xi. Sorry. Yes. Yes. And then we end up getting x transpose. Yes, that's fine. I'm cool with that. Oh, so even for the matrix. Oh, so yes, it ends up being the same. Okay. So for every entry in our gradient matrix, we have um partial of L equals yeah is times xi. Oh my goodness. I through D. Yeah. Input feature I. Okay. Yes, notice how the first two terms only depend on the class index. We group them together into a single scalar. Interesting. Or we can group them. Good. I'm going to emphasize that as an option. So in vector notation, the entire... Oh, because they all belong to J, you can turn it into a vector. Sure. In vector notation, that entire vector is the element-wise product of our two upstream vectors. Okay. Now our scalar derivative is simply... Oh. And that's the definition of the outer product. We're multiplying every element. Oh. Wait. Wait, that worked. I really like that. That's good. Man, whoever thinks AI not a good teacher, bro. I might make this the thumbnail. I was debating what... How do I say? I was debating what the thumbnail should be. Dude, this. Like, this is amazing. That was perfect. That made perfect sense for me. So hell yeah. Hell yeah. Um, let's see. Good learning for today. Um, I guess I can only do so much in an hour. I'm assuming today's video is an hour, like every other video. It's not timed. But I don't know. I assume I get tired after an hour. We'll see how long it is. Um, yeah, didn't make it to the LLM. That's unfortunate. One of my questions that I have for myself is like when we're going to get to the coconut stuff because I really need to get to that. I think maybe, how do I say, what's tomorrow? Tomorrow's Wednesday. I would say by, no, because I'm going to do something else on Thursday. I would say by Friday. Oh, well, I record videos on the weekend too. We have the rest of this week to do conceptual stuff. I think conceptual stuff is still like worthwhile. But Saturday, this weekend, I must touch code. No, I think this Friday. I want to touch code because this Friday I want to read code, and then this Saturday I need to touch the code. You know what I mean? Like, or maybe I do Saturday I read and Sunday I actually start coding something. But I know that it can't all be one day. I'm going to try to force myself to do too much in one day. So yeah, that was good. I really like that connection going from the single all the way to the cross, and like that actually connects the notation and stuff, and how we actually have ended up producing the Jacobian. So AI is not a bad teacher, and I'll see you tomorrow.